Hi, everybody. Welcome back to Chem 140. Let's see, what do we got coming up today? So we're gonna finish Unit 12, almost certainly. There's like 10 or so slides left. We'll get started on Unit 13 if we have time. And then there's a few things that are due tonight. So lab number 3, that's due tonight. Quiz number 6 also due tonight. Those are both soft deadlines, so if you can get one done, do the other tomorrow, you're fine. If you do both tomorrow, you're fine, of course. Just don't run out of time. When I make last call tomorrow, it will be for both assignments, and I'll have them both close at the same time. So make sure you get everything in before that deadline. What else do we have going on? There's not really much to mention. I think it's not next week, but the week after is Thanksgiving. So we're going to have a lab next week, but it won't be due for 2 weeks. So just a heads up on that. I'm not making something due on Black Friday. As much as Maya is going to complain to me about it, I just heard her meow. Oh no, I've addressed her. Now she's coming in. Maya, go away. No, stop. Yeah, I think that's it for announcements. So let's just get over here to this. Oh, you know what I need? I didn't get my tablet. Let me move my calculator here and my phone. And bump into a cat. What is this stuck on? There we go. My tangled mess of cords at my desk here. Let's see here. Yes, you're a cat. She wanted to let you all know that. Okay, cool. That works. All right, so what we're going to do today, in the class on Tuesday, what we were doing was turning quantities of things into moles. What we're going to do today is we're going to take that idea and present it with molecules. Now, when we look at molecules, molecules are just clusters of atoms that are stuck together. And so something like P2O5 here, you could split it into its constituent pieces, and now that looks like I just wrote poo-poo. This is great. This is a great example. You could split all of the pieces of any molecule apart. And I could say that in one molecule of P2O5, there is all this stuff in here. And so what I would do is I would say, well, there are 2 atoms of phosphorus. Yeah, this is why they pay me the big bucks, because I get to write poo-poo all over my slides. There we go. I'm just going to sit here and laugh and snort at toilet humor. I'm sure this is how most of you feel about this class. Anyway, I have one molecule of P2O5, and here comes the cat. God damn it, everything's falling apart. This is the world we live in. I have one molecule of P2O5. I could say that in that one molecule I have 2 atoms of phosphorus and 5 atoms of oxygen. Like, those are true statements. So I could make equalities that resemble that. In fact, what we're going to do is go to this slide. And we're actually going to write that out. So, one molecule of P2O... Oh, there we go. So that statement for this molecule is correct. For every molecule of P2O5 I have 2 atoms of phosphorus. And I could do the same thing for oxygen here. Maya, stop it. Gosh. Now my cat is just... She's hiding behind things and just peeking out and going, meow. I'm still here, you know. All right. Now, what's the point of all this? Well, we don't want to work with molecules, right? Instead, what we want to work with are moles. So if I just multiply everything by 1 mole, this statement is still true, right? Because for every molecule, I get the same ratio of phosphorus to oxygen. So I could just do this. And so now I get a new statement. 1 mole of P2O5 has 2 moles of phosphorus in it. And 1 mole of P2O5 has 5 moles of oxygen in it. And these numbers just come from the formula itself. That didn't quite point at the coefficient on oxygen. There we go. So we can write statements that link a molecule to the pieces that make up that molecule. And that's the first step in figuring out what we're going to do today, which is to take quantities and relate them to other quantities by using this concept. Because all this is doing is counting. And when we want to make a ratio with counted amounts, we can directly compare things. We can't do that with mass. For example, an oxygen atom is heavier than a hydrogen atom. It says so on the periodic table. An oxygen atom weighs 15.999 AMU, and a hydrogen atom weighs 1.0079 AMU. Those two are different masses. So if I give you 10 grams of each substance, I'm going to have way more hydrogen atoms because hydrogen is so much lighter. But counting numbers is something that we can do to make equivalencies. So this is how we're going to compare different entities together by how many there are. And the way that that is done is by using moles. Now, if a lot of that just didn't really make sense or it sailed right by, that's okay. You're going to understand what that meant, what that statement meant of like using ratios to count and convert between things as we do these problems. All right, so let me clear this out of the way because the slide is just going to make these ratios for us. Oh, I guess it's on the next slide. Okay. So here's an example problem. Let's go back to this slide that I can write on. And what we're going to do is we're going to answer how many moles of oxygen atoms are in 2.5 moles of P2O5. And if you're saying, well, I'm just going to take that number and multiply it by 5, you're exactly right. That's exactly what you want to do. But let's show why that works using dimensional analysis. So I have this as my quantity, and I want to figure out how many moles of oxygen are in that. So that means that if I'm writing out my little blueprint here, this thing that we've been doing all quarter with these types of problems, I know that the ratio of O to P2O5 is right here. That in a mole, actually, let's do that in a different color. In 1 mole of P2O5, there are 5 moles of oxygen. So when I do my dimensional analysis here, I could set up my units in this manner. I could say moles P2O5 and moles of oxygen. I can make this relationship so that those units cancel out and leave the units that I want. Now all I gotta do is fill in the numbers. Well, there's 1 mole of P2O5 for every 5 moles of oxygen. And that's how you end up just multiplying by 5 here. So 2.5 times 5 is 12.5. So that's a really straightforward example. Now, you can do this with any amount of starting material and any formula you want. So if I wanted to just make up an example problem, like, say, I think the next slide has DNA on it or something, deoxyribose, after more of these examples. But the process is the same. Take the amount that you have and then set up the units so that you get the unit that you want using the mole-to-mole ratio. So for this practice problem here, and this is going to fall off of the domain of the capture. There we go. For this problem here, we had to make new ratios. And after a while, you'll just start looking at the formula and be like, oh, I don't need to make ratios anymore. Like, that's fine. So let's start by writing the ratios between the molecule and its parts. So I would say in 1 mole of the original thing, how many moles of carbon would there be? What number should I put in front here? Let me know what you think. Exactly, it's 3. Where did you get the 3 from? Yeah, it comes from right there. And if I wanted to write these sorts of statements for the other molecules, or I'm sorry, the other atoms in the molecule, what could I get out of this? So 1 mole C3H6O3 equals how many moles of H? Yep, perfect. Just because there it is right there. And then again, we could do the same thing for oxygen. So making these ratios is going to be important to solving these types of problems. So let's solve the problem. I have 1.2 moles of this stuff. And I want to turn moles of whatever molecule this is into moles of carbon. So let me set up my units to do that. Moles of C3H6O3. So these cancel. We're going to turn that into moles of carbon. Now, which ratio... That was the worst arrow ever. Which ratio allows me to answer this question correctly? So, in one of these, how many carbon are there? Well, since we wrote down all the ratios, you know that, oh, hey, here we go. Because it comes from that number in the formula. So there you go. So when I now do the calculation, I get 3.6 moles of carbon. Remember that moles are a unit of counting. You can think of it like a dozen. Except instead of 12, which is a dozen, a mole is 6.022 times 10 to the 23. So think of it as like a really, 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 really big dozen. Kind of like if you were selling donuts, I could say, okay, if I have 1.2 dozen donuts, and inside those I have 3 of some type, like how many of that type do I have? And you would have 1.2 times 3 dozen. Do you know who would like a mole of donuts? Mole of donuts. No, I don't know anyone like that, actually. Anyway. So that's how we solve these types of problems. When I give you a formula and a starting amount in moles. But what you're going to find is that we don't really start with moles very often, because that's not a unit that's easily calculated from like tools that we have. So like, for example, if I go to the balance and I were to put sodium chloride on there, it doesn't tell me how many moles I have. It tells me how many grams I have, because mass is much easier to count. So we're going to be turning all of these moles into masses or numbers. Like, maybe I want to know how many atoms or molecules there are. So these are all possibilities that we can explore. I got the second problem on here, so I'm going to just do this. Now, this question's a little bit different. This is just asking you how many atoms of any type are there in this molecule. So it doesn't care about carbon or hydrogen or oxygen. It just says that when you break this molecule into all its constituent pieces, how many moles of pieces do you have? So if I wanted to make a ratio like that, I would have to do something like this, and we'll do this in purple. In 1 mole of C3H6O3, how many moles of atoms of any type are there? You wrote down 12 really quickly, and that's the right answer. How'd you get 12? What'd you do to get that? Added what? There's a bunch of numbers on my screen. Yeah, there you go. So you just added the... Oops, I didn't mean to cross it out. So you just added all of these things together. If you imagine like a model of C3H6O3, like it was a tangible thing where you had all the molecules and they were all like held together by toothpicks or something, and you pulled them all apart one piece at a time, you would end up with 12 things that represented atoms, because 3 of them would be carbon, 6 of them would be hydrogen, and 3 of them would be oxygen. So knowing that, what I can then do... Oops, I'm out of space here, aren't I? Let's do this. Knowing that, what we can do is we can say, if I have this many moles of my starting material, and I turn moles of that into moles of, we'll just call it atoms. First of all, these units cancel out, so I now have the units that I want to solve the problem with. And then I can use this number up here for my ratio. So I could say, okay, in 1 mole of my starting material, there are just 12 moles of atoms, and that number comes from, again, all of the numbers added together. So 1.2 times 12, that should be 14.4, but we only get 2 sig figs from this. So that's the answer I'd report. This one's counted, so it's exact. Did my answer pop up on there? No, it hasn't yet, so let's just do that. Alright, do I have more of these? I don't. Okay, so let's have you try some of these. So this is deoxyribose. Deoxyribose is a carbohydrate that is the sugar part of the backbone of DNA. So DNA alternates between sugar and phosphates. So remember phosphate, that's one of the polyatomic ions that you need to know. And then attached to the sugars are nucleotide bases, which are like imines and things like that. If all these words sound sort of familiar, it's because I've probably said them at some point. You're going to talk about these a lot more in OChem if you go that far. If you're a biologist, you're going to talk about them all the time because DNA is important. Let's suppose I gave you 0.377 moles of the sugar that's used to make DNA. How many moles of each type of atom are there in that sample? So what I mean is how many moles of carbon, how many moles of hydrogen, and then how many moles of oxygen. Not just how many summed together. So do these three separately. Report your answers in the chat, and when I see a few answers there, we'll go over them together. I'm going to fill my water, and I'll be right back. So see you in a bit. All right, I see a bunch of answers coming in, so please finish up in the next minute or so. All right, let's click on that. Oops. There we go. So let me clear all this out here. That's not how I delete, that's how I select the cursor. There we go. All right, so now you can write out all of the mole statements, and I'm going to do that just to have it on the screen for people who are watching this later. And so here's our ratios here. And this is just the same thing going down here. I'll just do that, I guess. I don't know. And so, again, we're going to put the number that corresponds to the coefficient in front of it. So for 1 mole of C5H10O4, there are 5 moles of C. There are 10 moles of H and 4 moles of O. So now I can just take these ratios and multiply them by the amount that we're starting with, 0.377 moles of C5H10O4. So for the first problem, I want to know how many moles of carbon there are in there. So I would take my units and set them up like this, so that everything cancels out to give me what I want. And then I just got to pick the right ratio, which would be this one. So I'm going to put the numbers in like that. And when you times 3.377 times 5, you get 1.89. We could do the same thing with the other two. So let's do that. In fact, you know what I'm going to do? I'm going to do this. That's not what I'm going to do. That's not how that works at all. Hold on. There we go. Well, let me make sure that that actually copied. There we go. Oh, that was Steve. Not that you can hear that, but I just was like, ah, ding. I have the audio muted. There we go. That probably took more work than just writing it out twice, so you never know. So let's see here. This one will be moles of H, and this one down here will be moles of oxygen. Steve, stop messaging me. So 10 moles of H, which would be, that's just this times 10, so there you go. And then for the last one, we would put 4 moles of oxygen. And that one I can't do in my head. So let's see here. 0.377 times 4. 1.51 moles of oxygen. There you go. So that's how we do that. But before we go on to the next topic, let's suppose that instead you wanted to know the number of grams of carbon for your answer. So I say, I give you 0.377 moles of deoxyribose. Of that sample that I've given you, how many grams of carbon are in it? Could you answer that question? Not rams, but grams. Yeah, the mass. And yeah, you would multiply by the number on the periodic table, right? It's atomic mass. And so that would convert from moles to grams. What if instead of giving you moles here, I gave you grams of deoxyribose? That's not an H. There we go. So, for example, I said instead of 0.377 moles, I gave you 0.377 grams. Well, what you could do is drop the pen. There we go. You could turn it into moles and then do this process. And so what you're going to see here is that this mole to mole conversion is sort of the bridge between what we did on Tuesday and what we're learning about today and what we'll do in the next section. Okay, so let's move on to that and see that in practice. So the whole point of this chapter is to get you used to doing these sorts of calculations. And if you can make it here, you can make it anywhere in the rest of the quarter. Like, it's all basically different ways to do this calculation. So this is probably the most important of all the sections that we're going to cover for math here. So make sure that you're asking me any questions that you have while I'm here, obviously. If you're watching this video later, send me an email if you need anything. All right. Yay, math. That's everyone's favorite, right? All right. So you'll remember that we could do this from before. So if I wanted to know how many atoms or formula units or whatever were in a sample, I had to use Avogadro's number to convert from moles to amount. And we also know that if I wanted to figure out the mass of something from its moles, I go to the periodic table, or P table online, or whatever it is. And I take that number and I multiply or divide depending on which direction I'm going and how the units work out. But in the previous section that we just covered, we learned that you can turn moles of something into moles of something else. So we'll call this, I don't know, Q or something. So what that means is that if these moles on the left here can turn into grams and particles, and these moles on the right here can turn to grams and particles, I now have a way to get from any part of this grid that I've made to the other. And so now I can ask you questions such as, in 20 grams of aspirin, how many of those grams are oxygen? You can answer that now. You know how to do that. In a 1 gallon jug of water, how many grams of water are hydrogen? You can answer that now. You can do all of these crazy types of questions based on this unit alone. And so it's a really powerful tool. And so that's what we're going to be doing. Now, this chart is super useful. I don't know why I have 2 slides that just like, here's the chart slightly moved upward. Yeah? Like, whatever. We're going to have this chart on the screen so that you can follow it. But more or less, you should just consider this to be a blueprint, like those blueprints that we've been making all along, where I go like, oh, I want to turn feet into miles. So I'm going to do that with 1 conversion. On these, I've already made the chart for you. So this chart is helpful to have handy, and you just move around on it. So let's suppose that I got to get a different color that isn't any of these colors. So let's do purple. There we go. Does that show up? It does. Okay. So let's suppose that I give you a mass of water. So I'll just write a sample problem down here. So let's say I give you some amount of water, and I want you to tell me how many atoms of hydrogen are in it. For all of these types of problems that we're going to see, the thing that you are looking at, we're going to call it either A or B. And all these A's and B's mean are the two things the same? If they are the same, then you stay on that side of the bridge. But if they're different, see, water and hydrogen are different, we're going to have to turn moles of water into moles of hydrogen. So for this specific problem, A is water and B is hydrogen. So think of just A and B on the chart as a variable. Now to solve this problem, since I gave you a mass, what our strategy would be, okay, here's where I start. I have a mass of water. I'm going to turn that into grams of water. I'm sorry, I'm going to turn that into moles of water. Once I know moles of water, I can then turn that into moles of hydrogen. And then finally, I can figure out how many atoms of hydrogen are in the sample. For each of those steps, that will be a conversion, and the conversions use the exact same numbers that you have seen used already. So when you're going grams to moles, you use the periodic table. When you are going moles to moles, you use the numbers from the formula. And when you're going moles to particles, you use Avogadro's number. So this section really is nothing new. It is just synthesizing everything we learned on Tuesday and what we just learned earlier today and putting it all together into one big calculation. And pretty much for the rest of the period, that's what we're going to be doing, is doing problems like this. And my intent is that everybody can do them. So let's do an example. Actually, let's not do that example just yet. Let me make up an example with the water here. There's a reason I don't want to do that first example. I don't know why that didn't select all. Am I on a new layer? I am. Because I copied and pasted. Alright. So what I'm going to do is, scroll off the paper. I'm going to make a problem for you that uses the strategy that we just did. So I'll say in 25 grams of water, how many H atoms are present? So if I go like this, this should work. Let's see here. Control print screen. And then I should be able to just paste that in here. That kind of worked. But that's way too big, so hold on. Oops, hold on. I gotta lock the ratio so it doesn't get ridiculous. So we'll just kind of stick this over here. There's our chart. I would put it up in the little like thing above, but that will just, to make it visible, I would have to eat up most of the screen. So apply the transformation. Yes. All right. So our strategy is to start with the mass of water, turn it into moles of water, figure out how many moles of hydrogen are in that sample of water. And then once I know how many moles of hydrogen there are, I can figure out how many atoms of hydrogen there are. So let's do that. Let's set up the calculation. We'll do that down here in this big space. So I'll start with this number because you got to start with what you know. I'm going to turn grams of water into moles of water. And I know how to do that. I have to go to the periodic table. I can then turn moles of water into moles of hydrogen. And I know how to do that because we just did the section on ratios between molecules and the parts in them. And then once I have moles of hydrogen, I know how many atoms are in that sample. So when I'm done, this will be my answer. So now that I've got the problem set up, all the units have canceled out to give me what I want by following the flowchart. Now we can do the numbers, right? Just like we've been doing before. Do all the units first, and then do the numbers. Okay. How many grams of water are in a mole of water? Well, where do you get this information from? Well, you go to the periodic table to get the atomic mass, right? And that should be review. The other place that you can go is Lentech. So if I go to here, that's the EVCC class schedule. I don't actually want that. Lentech. I'm just seeing how many people have enrolled in my class next quarter. Which is surprisingly a lot, actually. Window capture. Capture Lentech. There we go. That's not actually going to capture it. That's... Oh, I just scrolled it off the side there. So you can see in the middle here, the molar mass of water, my cursor wasn't showing up, is 18.02. And again, you get that by just adding the numbers on the periodic table. We've done that plenty, so we don't need to actually do that. Okay, that ratio is taken care of. Let's go to the next one. How do I do the ratio between water and hydrogen? It's already in the chat, so we'll just do that. For 1 mole of water, there are 2 moles of hydrogen. That's what we did in the previous section of today's lecture. And then finally over here, in a mole of hydrogen, how many atoms are there? Well, in a mole of anything, how many of that anything are there? It's just Avogadro's number. Last thing you gotta do is put it in the calculator. Now, you do need a scientific calculator for this because you're going to be getting numbers that are extremely large when dealing with atoms. Your kitchen calculator won't be able to do more than 8 or 9 digits, and so you'll get an overflow if you do that. If you don't have a calculator handy, remember you can use Wolfram Alpha. It's really good for that, and it will show you what it thinks it's trying to calculate. And you can correct it if you make a syntax error or something like that. But if you don't have a calculator, please let me know so that I can send you the link to Wolfram Alpha if you don't know where to look it up. Because you will absolutely need it for the rest of the quarter. So this is the general flow of this type of problem. Now, something that can happen is I might give you a problem that resembles something from earlier in chapter 12, and maybe, for example, let me change my color here to, let's do that. That'll show up. So let's suppose I start with grams of A, but then I ask you how many, particles of that same substance there are. And I'm actually going to do that on the next slide here. So you have to be careful that you know where you're going on the little chart. Okay, so read the problem carefully because this problem shows what happens if you go down the wrong trail. So I have a sample of vitamin C, and I have a mass And I want to know how many vitamin C molecules there are. Now you'll notice that both the number that I give you and the thing I'm asking you to solve for are the same thing. So what that means is that that's not going to work. What that means is, here's my mass that I'm starting with. Here's the amount that I want to find. I'm just going to go like this, and then I'm done. I do not need to do this part. In other words, this is the sort of problem we were doing on Tuesday. Okay, so those problems still exist. Be very careful when you see a problem that it isn't one of the old style problems, because if you try the new stuff that we're doing and you think, oh, I'm going to convert this into moles of something else, and you're going to find out that, like, oh, well, what the heck do I do here? And most students, when they get to that point and don't know what to do, they just start to write any number they can think of. And of course, that's going to lead you down the wrong path. All right, so let's do this problem. That's already captured, so that's good. Let's get rid of all of these things. That's on a different layer again. Oh my goodness. Too many layers. Delete layer. Delete layer. Select all, delete. There we go. All right, so I'm going to, oops, not write in sky blue for one. That's hard to see. I'm going to make our little chart here. So I started with a amount in grams of vitamin C. And our objective is to figure out the number of molecules of vitamin C. According to our chart, there isn't a direct transition, but I can turn grams into moles. And then moles into molecules. So that's what we're going to do. So for our first step, we'll turn grams into moles. So grams of vitamin C into moles vitamin C. So molecules or particles? Yep, molecules or atoms or formula units. These are all particles. And I don't know if I can write sideways, but I'll try. There we go. So that box that's marked particles, that's a good question. So that box that's marked particles works for anything you're going to count. But I don't have one specific term that describes them all better than, like, particles, unfortunately. So we turn grams into moles here. And then we'll do our next step, which is to turn moles into molecules. That's the unit that we want. So now we can do the numbers. So I got grams and I got moles. How do I convert from grams to moles? Got to go somewhere. Where is it? Do I go to Avogadro? Do I go to the internet? Do I go to the bathroom? What do I do? I said bathroom, and then I thought about the poop joke from, like, the first minute, and I was like, no, I'm not going to go do that again. I'm not going to start laughing. What is the formula? C6H8O6. So what did you get for grams in a mole of vitamin C? Tell me what you get, and then we'll compare it with what I got. $176.124. Yeah, that's what I have too. So let's write that down. So in 1 mole, there are 176.124 grams. Now, if you don't have that extra 4 in there, odds are it's probably not going to affect our calculation because we're only going to be good to 3 sig figs anyway here. And then over here, in this last calculation, in a mole of vitamin C, how many molecules are there? Where do I go for that? What was the website called again? It's called Lentech. Let me just paste the link that I have. Lentech calculator. So this is the link that I use for a molecular weight calculator. Mostly because I think it was the first one that came up when I looked for one. I've used this for years. And then the name got stuck in my head. So instead of typing molecular weight calculator, I just type Lentech. Like they're a water treatment company or something like that. So all right. Anyway, for this relationship here, for moles to molecules, there's only one number, and that's Avogadro's number. So punch it all in the calculator, see what you get. That should be a 2, but there you go. 8.54 times 10 to the 20th molecules of vitamin C. All right, so what we're going to do is we're going to take our break now because it's about that time. Let me see here. Yeah, we're just about there. So let me put this on the screen here. Let me get the timer out. Where is my timer? There it is. Boop, you're going to ask me to update. Maybe not. Okay. All right, so I'm going to hit this. Let me turn the... Oops, I got to move this out of the way. Turn the music back on. And we'll play some more Overdin for you. And we'll be back in a little bit. So see you soon. Alright, I'm back. Let me see. Let me just close some windows here, because I don't need these soundtracks open anymore. I don't know how to describe Oberdin besides 18th century insurance claims on a boat and crazy ass murder mystery. And it seems weird that putting those two things together would equal this is probably my favorite video game I've ever played. So, if you like puzzles and aren't afraid of a game that has exactly one color, seriously, it's a 1-bit game. There's the color that is drawn in the background, and it's still beautiful. Um, Absolutely play it. Like, I cannot recommend it highly enough. Just in case, the author says, "Oh, this guy is playing my music." Um, it's like, I'm gonna copyright strike him. Oh, he loves my game. It's okay. All right, so what are we doing now? We're going to do more of these problems. So let's do another one. I'm going to give you caffeine because you guys need to wake up. That's just the joke that I tell. I'm going to give you 100 milligrams of caffeine. That's a lot of caffeine. Don't take it all at once. How many of those 100 milligrams are nitrogen? You can actually solve this problem, but I'm going to do it with you just so you have another example under your belt. What I am going to do, though, I'm going to go print screen. And then go to Photoshop over here. Let me clear this out of the way. Then I will just take this part. Cut. Boop. I put a new layer. Oh, did okay, cool. There we go. That's the part that I want. All right. So, what do we do here? What is the problem giving us to work with? What is the problem asking us to solve for? And how do we get from A to B? I realize there's some delay between me saying that and you guys possibly typing in your answer. Let me write down what I know to start. Let's ask, what is the amount that I was given to start with on the chart? What would that be? Is it particles A, moles A, grams A, particles B, moles B, grams B? Where do I start on the chart? So I want to start by doing grams to molar mass. So that means I got to start here, yeah? So this is where I'm starting. And obviously we're going to go this way. And then once I know the number of moles that I have, what will I do with that? Then we'll turn it into moles of the other thing. So if this side is caffeine, this side must be nitrogen. And then we'll turn it into a mass of nitrogen. Good. So there's our strategy. That's what we're going to do. We're going to start with the mass. We'll turn into moles. We'll turn the moles of that caffeine that we have into moles of nitrogen, and then we'll turn it into grams of nitrogen. So grams of caffeine, moles of caffeine. Those cancel out. Moles of caffeine. We'll then turn that into moles of nitrogen, just like our chart is directing us to. And I ran out of room, so we'll just do the last one down here. Moles of nitrogen, grams of nitrogen. All right, now we got to go looking up those numbers. So let's do that. So how many grams are there in a mole of caffeine? Obviously, you need to know the formula of caffeine in order to do that. I've provided that for you on the screen at the very top there. So it's C8H10N4O2. I got 194.19. So whatever method you're using, keep doing that. But then double check that you got the same number that I got. And that I didn't say swap two numbers or transpose them. Alright, now that I've got that one taken care of, I need to find the number of moles of caffeine and the number of moles of nitrogen. Well, the formula is up here at the top here. It's above the arrow. I can't draw in that interstitial space. But what's the ratio between nitrogen and caffeine? What number do I put on the top here? There's a lot of numbers out there. Which one do I pick? 4. Yeah, very good. Because that's the number that tells me how many nitrogens there are in the caffeine molecule. This is also a good test to see what my ping is, because if I ask an easy question, everybody answers that really quickly. And it takes like 20 seconds. So I'm like, okay, I have that much delay. Finally, how do I do the relationship between moles of nitrogen and grams of nitrogen? Where do I go to get that information? Yeah, it's just the molar mass of nitrogen, yeah? So according to the periodic table, that is... I think this is right. I'm doing this from memory because my periodic table is under my monitor. I have like a little like nook that I just shove papers under, and my table is there. Yeah, 14.007. So let's multiply all these numbers together. Now, when I do this, I cannot get a number that is larger than 0.1 grams, because that would imply that I have more nitrogen than I do caffeine. So obviously you know the upper bound. It can't be more than 100 milligrams. So the answer that I got was 0.02885. I only get to keep 2 sig figs, so there you go. Or 29 milligrams of nitrogen. Actually, what I'm going to do is I'm going to go back to this slide, and I'm going to let the little animation that it's not really an animation. I just hit a button. But you can see that so first we identified what we're starting with and where we're ending, and we figured out how to get there. And then we got the answer. All right, let's do another one here. I'm going to give you adrenaline, and I'm going to give you the same 100 milligram sample. How many atoms of hydrogen are in the sample of adrenaline? So this is the water problem that we did earlier. But this time, I'm going to have you do it. So what I want you to do is on the little chart here, figure out where you're starting at, figure out where you're going, and then convert your answer to the correct units along the way. Oops, I didn't mute the audio, so you heard Steve message me that time. I saw the audio spike there. So go ahead and try this problem. And in about 3 minutes, I'm going to put the answer on the screen, but I'm going to let you keep working through it. And then we'll go over the answer together after about 5 or so minutes have elapsed. Okay? So good luck. We're all counting on you. See you in a bit. All right, 1 or 2 more minutes, and then we'll go over the answer together. Let me put the answer on the screen here, just so you can check it if you have finished. But we'll go over this together in just a second. All right. That didn't quite... There we go. And that's not actually what my screen shows me. There we go. Okay. It just hadn't updated. All right. So, if this works correctly now, I should... Oh, I can't draw behind it, though. That's not going to help me. I was going to say, if this works, I should be able to just delete everything, but I got to move the layer. Okay, there we go. Now I can draw all over it, and that will go away. Oh, my undo doesn't work anymore. Because, of course, it doesn't. Oh, no, never mind. There it goes. All right. So let's work on this. First, we got to figure out what we're starting with. I was given 100 milligrams or 0.10 grams of adrenaline. I'm just going to abbreviate it that. So that means we're going to start here. First step is going to be to convert it to moles. You're going to find out that the first step is almost always convert it to moles. Then we'll turn it into moles of the other thing we're looking at, which would be hydrogen. And then we can turn... Oops, not grams. That's wrong. Boop. Can I go backward? I guess I can't. Sometimes undo doesn't work on Photoshop, and I don't know why. Probably because I'm bouncing back and forth between windows. All right, so let's follow our little plan of approach here. So we got grams of adrenaline, moles of adrenaline. Units cancel out. Got moles of adrenaline, moles of hydrogen, because that's what the problem wants us to answer. And then we got moles of hydrogen and then atoms of hydrogen. Those cancel out. And that'll be our answer when we're done. So let's do the numbers. How many grams are there in a mole of adrenaline? If someone knows for me, let me type it in the chat. Otherwise, I'm going to type it in here. Oops, that is covered up. C9H13NO3 is 183.20. There you go. In 1 mole of adrenaline, how many moles of hydrogen are there? The coefficient is 13 in the formula. And then in a mole, how many atoms are there? There are Avogadro's number. We punch it all in the calculator. Don't forget this number over here because it's not in purple, but you still got to use it in your calculation. And I got 4.3 times 10 to the 21. That looks like what other people got. So we are all set there. All right, good job. Do I have more of these for you? I think I do. Oops. Doesn't work if I'm not on the right screen. Oops. Get surprised by my sound effect there. Here we go. So here's the last one. What I want you to do is determine the amount of each of these quantities based on this starting amount of 0.522 grams of iron 2 iodide. Okay. Now be careful because I'm asking you for different things each time. So you make sure that you're solving for the correct thing. Okay. All right. So I'm going to give you 5 or 6 minutes to do these. And then we'll go over the answers. So I'll see you in a bit. Type in the answers once you got them in the chat. How are we doing? If you have any answers, please enter them into the chat just to let me know how far along you are and if you need more time. Obviously, you need more time because there are 4 problems instead of 1. So I'm going to let you keep working. And please let me know if you have any questions. All right, let's go over the answers here. So, let's see here. That's good enough for now. Let's see if this does what I want it to. Boop. Okay, good. Look at that. Only erase the things I want. Technology. All right, so for the first problem, we're going to do the first problem in red. Well, sort of. So, we're going to start here for all of our problems, and then we're going to move to somewhere else. So here's where we're going to go for the first problem. We're going to go to moles, to particles. So we'll turn grams of FeI2 into moles of FeI2. And then we'll turn moles of FeI2 into particles of FeI2. Technically, these would be formula units. And I would use an abbreviation for it, but you could probably see why I don't want to do that. So, well... Alright, so there's our numbers, or there's our units. Let's cancel out. Let's do the numbers. I just looked this up, and I've already forgotten what the number was. 309.65. Not that I'm afraid to say FU on the stream. It's just that, well, Mark might be here evaluating me, and I probably shouldn't. Excuse me. What else we got? This is Avogadro's number. Forgot my decimal point there. There you go. And the number that was in the chat is correct, so I'm going to skip typing it in my calculator again. 1.02 times 10 to the 21 formula units. I guess instead of writing FU, I could write FUN, so it's fun. It's not an obscenity, it's entertainment. Formula units of FeI2. There you go. Okay, that was the first problem. Second problem, which I will change the color to... Let's get a dark orange going. Well, that's more brown, I guess. So for this second problem, we're going to go over here. And you're going to notice that for a lot of these problems, F is for formula units. Unless that was jokes. I apologize. You're going to notice for a lot of these, we're going to be starting in the same spot. So all of this part of our calculation is just going to be the same every time. Let's try that one again. And I'm gonna copy the part that's the same. Like normally I would do the numbers first, or not the numbers first. I'd do all the units first, and then do the numbers. But this part right here is all going to be the same every time. So what I'm going to do is write it all out. I don't know why that's not letting me select. There we go. We're just going to copy that. We're going to paste it a few times down here. Because we're going to use it again. All right. So now the next thing that we're going to do is, now that I have moles of FeI2, for the second problem, it's asking you how many moles of I are present. That's not the pen. So okay, as long as that's working. So there we go. And now I can fill in the numbers here. For every mole of FeI2, there are 2 moles of iodine. which means that when I punch that in the calculator, and the number that was in chat was also correct. 3. Oops, I forgot a 3. There you go. For the third problem, which we'll do in green here, so I want to go grams of FeI2 over to grams of Fe, it looks like. So when I go down to this problem, again, the setup is the same at the start, but I'll get to this point, and I'll want to do that instead. And then to get a mass of iron out of that, I just figure out how many moles there are and turn it into a mass. And we're all set. Ooh, that's a weird error. Oh, it took away my color. That's okay. All right, for every mole of FeI2, there's only 1 mole of iron, so this is just this. The only reason that we put those numbers in there is so the units go away. Mathematically, it doesn't do anything. And then how many grams of iron are in a mole? I think it's 55.845. Yep, this one I actually didn't calculate. I just assumed that you guys were doing it right. And I got 0.0941 grams of iron. 0.094142. Yeah, so that's good. I don't remember what the last problem is. I gotta do this to it. Move that up there. How many particles of iodine are present? So for the last problem, we'll start here again and go this direction. Already did the first step. Oops. Since I want iodine, I'm going to turn it into moles of iodine. And then my moles of iodine can become atoms of iodine. Technically, they're ions because this is an ionic compound, but we don't have to be that specific. What's the ratio between FeI2 and then I? It's 2 to 1 because of this 2 right here. And then finally, if I'm counting the number of particles in any way, I do Avogadro's number. Now, this result here should actually be the same as this result up here, except times 2. So you should have gotten 2.02 or 2.03 times 10 to the 21 atoms of iodine. And that makes sense, because if I have the number of formula units of iron to iodide, and I split them all into their constituent parts, I should have twice as many iodines as I started with formula units, because each formula unit has 2 iodine in it. And I guess that does it. So let me hit this button so that when I go back over to here and hit this button, it will make the happy sound that gives us all the good chemicals. Hooray! Feel the good chemicals in our brain. All right. That's all we're going to do. There's not really much point in starting Unit 13 when there's only 10 minutes left. So we'll call it a day and start Unit 13 on Tuesday. There is a quiz for for Unit 12 by itself. So everything that we've done has its own quiz. And so that's going to get posted tonight. I'm going to immediately go and upload that. Because that quiz has been written. It will be due... I know, no heartbreak quiz, blah. It's not all fun and games in Chem 140. In fact, it's not games at all. And the fun is arguable, too. Do you know about what time last call will be tomorrow? I've been doing midnight, so there's no reason for me to change it at this point. So it'll just continue to be midnight. Not that I would encourage you to be up on a Friday night doing schoolwork. So, like, try and do it tonight so you can enjoy your Friday. Not that there's anywhere to go, it's a pandemic, right? But just out of principle, I feel like I should discourage you from staying up super late right up close to the deadline, unless you have something that just absolutely warrants that you need to. Try and do it tonight if you can, so that we can enjoy the weekend. You can live for the weekend, whatever the expression is. Thanks to everybody for coming out. I will see you all next week for Unit 13, and we are almost done with the quarter. Like, we're getting there. Blink and you'll miss it. That's kind of the story of this quarter. So, see you next time.